Hello everyone. In this video, we are going to look at one of the navigation methods or algorithms in robotics, which is called the Braitenberg Navigation algorithm. And it's kind of bio-inspired. It's a really interesting one, also similar to a neural network, which is linking the outputs and the inputs of the system together. So the main motivation for me was when I was working with CoppeliaSim and I brought this Pioneer P3DX robot in, and I look at the script of it. When I look at the script, I found that the navigation algorithm for it was called the Braitenberg. So let me bring you a new one. Look here. So if I look at this new one that I just brought in, look, and look at the script of it, you can see that it says it is trying to avoid obstacles based on the Braitenberg algorithm. And I said, okay, that's an interesting one. Let's go ahead and explain it. So that is what I'm going to do in this video. So what I did here is I basically added a bunch of obstacles in this room, from human to furniture to blocks and walls and everything to plants. And let me first run it for you so you can see. So it goes close to obstacles, then literally stops, goes around, and you can see that as it gets close to any obstacle, it turns away and keeps going. If there is nothing on the way, it goes straight. Otherwise, it turns away from the obstacles and it keeps going and does not hit anything. So I want to tell you about this interesting algorithm that is on it. And one thing that you need to know about this Pioneer robot is that it has 16 ultrasonic sensors, 8 on the front, 8 on the back. And the reason you have on the back is if the robot needs to go backwards, you want to make sure that it does not hit anything, okay? So if you look at the robot looks like this. And as I said, 8 sensors on the front, numbered from 0 to 7, and 8 sensors on the back, numbered from 8 to 15. And you can use all of this to get a feeling of whether an obstacle is on the back of you, on the front of you, on the left or on the right, and turn away from them or stop when you're reaching to them. Okay, and just explaining this Braitenberg. So what I did is I added some comments here in this script, and I'm gonna share it with you under video description. So I added some comments again, right? Because I wanted to explain exactly the purpose of each line. But first, let me explain the algorithm itself. So what is this algorithm? The first thing about it is it's a simple yet elegant way. And it kind of is similar to a simple neuron, basically. If you know about deep learning and neural network, this is kind of very similar to that. So if you consider a robot, a differential drive robot or anything, so let's say this is a differential drive robot and the 2 in the back are driving and the 2 on the front are driven. So the outputs of the system, right, of your control system is the RPMs that are sent to the motors, correct? Yes. So, and the inputs are the ultrasonic. So let's say you have 2 ultrasonic sensors. So these guys receive the distances, and based on these, or maybe you have some more on the left and right, from these, you want to, based on these input signals, you want to form your output signals. So the way this control algorithm works, or navigation algorithm works, you directly connect your sensors to actuators with what? With weighted links. And this is the part that I said is close to a neural network. So you're not going to create a state machine. You're not going to create a specific planner or explicit map. You just say that each one of these inputs from these sensors has a weight multiplied to that input, and then that weighted input is going to be directly sent to the output of each motor. Okay, So the only real thing you need to do is to decide the weights of these inputs on the corresponding outputs. So if you have 2 inputs, 2 outputs, you can at most have 4 connections here. And for each one of these 4 connections that are shown by these black arrows, you need to come up with a weight, right? In general, if you have N sensors and M motors or actuators, you need to come up with an N by M matrix of weights. Okay, and you can add some constant or some biases, and that is exactly similar to a simple neuron. So it's the design, it's what you need to do. You need to design these weights. If you design them well, the system will behave properly and does the navigation. And I'll tell you exactly how it is done in this example. So first thing you need to do, you want to normalize all of the sensor values, normalize them into the range of 0 to 1, just to make sure the effect of all of them is similar on the outputs and not different, right? Because if one of them seeing a distance of, I don't know, 5 meters and another one is seeing a distance of 2 centimeters, then of course the one that is not seeing the object close have literally a lot of effect on the motors, and this one that is very close to the obstacle and has a small reading, it will have very small effect on the motors, and that's not how it should be. So you really try to normalize them first. Okay, it's the weight that tells you which one should carry a bigger effect, basically. And so you see here, I highlighted for you, the weights are not calculated analytically, they are designed or tuned experimentally so they can produce the desired effect. So the command, the RPM command for each motor can be determined as a baseline motor command. This is like your bias term. And then sum of what sensor values multiplied by the weights, right? So if the sensor value is shown by X, and the weights are shown by W, right? You can do a summation of WIXI, right? And then plus this constant bias. And this is like the output. And again, this is like a simple neuron. Now, what can you do here? What can you really do with it? So, this baseline motor command, if you don't receive anything from the sensors, right? So the objects in the environment are far away from the sensors, because each sensor has a range. These sensors can only see from so much to so much. The range is not infinite. So if the obstacle is outside the range of this sensor, so basically nothing on your way in immediate distance, then this baseline motor command is what you want your motors, your robot, to move with that forward, right? And if you pass that to both of the right and the left, the same baseline used for both left and right, this is also going to be V of the center of the chassis, and that is, as I said, how fast you want to move forward when there is nothing on your way. So when there is something on your way, you want to slow down. And slow down means these omegas here, or these V's, you want them to go down. For that reason, these weights, they should be negative numbers. This baseline is a positive big number, and these weights are negative numbers to reduce the speed. Okay? Now, if you can reduce the right a little bit more than the left, so the right goes like this, and the left still close to whatever it was, of course, you're going to turn to the right so you can avoid this obstacle. And the other way around, if you make the left more reduced than the right, then you're going to turn to the left and you can avoid an obstacle that is here. And if the obstacle is right in front of you, then you want to reduce both of them, but similar amounts, so it doesn't turn. Just you want those W's to be big enough so when you get very close to it, literally this whole motor command becomes negative. And since you don't want them to be negative, you can either saturate them at 0, so that's one way, so you can stop it, or negative means basically start going backwards. But if you want, you can just put saturation on this whole thing and set it to 0, right? So you can pass this whole thing now to basically a function like this, correct? A step function, so that when it's negative, it doesn't do anything. When it's bigger than or positive, then it produces a 1, and this is a 0, correct? So you can saturate it if you want. And that means completely stopping the system. So there are two terminologies that are used in the Braitenberg algorithm. One of them is called phototaxis or attraction. And phototaxis means basically your object is going to move toward a target, okay, where these W's could even be a positive if target is not an obstacle and your goal is to just go toward an object. And the other one is what we call the anti-phototaxis, or a repulsion, basically, where the goal is to move away from a target. In that case, target is not really a target, it's an obstacle. Okay, and another thing I want to mention is there is not really one algorithm for Braitenberg navigation. In general, we call them Braitenberg machines, and there are a lot of different algorithms and a lot of different methods for setting these weights, basically heuristics and so on, for achieving different results. Remember, we said that we can tune them so they can achieve the kind of behavior that you like. So if the behavior is obstacle avoidance, then, as I said, you have to set these weights to negative numbers. How do we do that? We're going to see. But if they are attraction, we can set them to positive and so on. So depending on what kind of behavior we want, we can get different machines, tune W's differently, and get what we call different Braitenberg machines. At the moment, the goal is to avoid obstacles. That is what we want to do. So if you look at in this code that I showed you, these are the weights that are considered for the 16 sensors. As I said, 8 of them are in the front, from sensor 0 to sensor 7, where 0 here is right next to the left tire and 7 is right next to the right tire, and there are 8 on the back, okay? So these are the weights that are given to the sensors in the front and in the back. And if you look in both of them, left and the right motor, their velocity commands for them, the weights of the back sensors are all 0. What does that mean? Means that this robot never wants to move backward. It only is going to move forward. So I'm never going to use these sensors in the back. For that reason, I can say what? I can say, hey, I don't even need to read these sensors. So although I get data from them, but I'm not going to use them, so I set a weight of 0 to them. That literally means turning off those sensors, basically. Yes, but inside the software. Now, how do I use these front ones? So these 8 ones that are on the front, how do I use them? Remember, the first number corresponds to sensor 0, the second number corresponds to 1, all the way to this last one, which corresponds to sensor 7. So let's take a look and see if these numbers make any sense. For the left one, as you can see, as I go from 0, which is on the left, as I go from the left to the right, for the left motor, look at what happens. The weight of the sensor that was just on the left side, on the motor side, is the smallest negative number. And as I go to the sensor that is on the other side of the motor, as I go this way, it becomes a bigger negative number. Okay? And if you look at the right motor also, for the right motor, the sensor is sensor 7, this one. The right motor is where this sensor is. Again, you can see it's the smallest negative number. And as for the right one, I go from right to left. I go from sensor 7 to sensor 0. Look, again, the numbers get bigger negative numbers. So the behavior is exactly the same. If a sensor is on the same side of the motor, give it a small negative weight. As you go toward the other motor, give them bigger negative weights. Why does this work? Let's take a look at some specific scenarios here. So scenario one, there is an obstacle right in front of the robot. Okay, if there is an obstacle right in front of it, which one of these sensors do you expect to receive the signal? Yes, you are right. You probably say sensors in the middle. Sensors 3 and 4 are the ones that are going to get probably the biggest signals. These other ones are probably not going to get too much. And where are sensors 3 and 4? If you look at them, right, this is 2, this is 3, this is 4. So for the left one, the weights are negative 0.8 and negative 1. For the right one is negative 1 and negative 0.8. Yes? Okay? So what's going to happen? Since these are the same number, you see, it's just the order is swapped. Assuming that it's right perfectly in front of it, since these two guys are perfectly in the front, they should get the same strength signal. So this one should get X. This one should also get X. So in that case, what would you get? The signal here is going to be the base command, V base, right? V of the left, if we follow this formula, and assuming that these other ones are all 0, V of the left is going to be V of the base minus 0.8 times X minus 1 times X. So it's going to be minus 1.8 times X. And the exact same thing for V right. V right is also going to be V base minus what? 1.8 times X. It's just negative 1 times X minus negative 0.8 times X. They get the exact same thing. So what happens? Both of them are slowing down and at the same rate. So you're not going to turn left and right, you're just going to slow down. And when you get what? When you get too close to it, then hopefully this number is big enough to completely make this whole, both of these numbers negative. And once they are negative, guess what? If you saturate them, the robot is going to stop. If you don't saturate them, it should start going backwards. Yes, but in this case, we don't want this guy to be going backward. So the ideal thing is to basically saturate them with 0. Now, one thing that you might wonder is, when I get closer to this obstacle, this X should go down, right? Because that is my distance. When I get closer to the obstacle, the X goes down, it becomes a smaller number. That means this V left and V right get bigger. So ideally, you should not move too much, but as you get toward the robot, you should speed up, which is not exactly what you want to do. So if you want this to operate properly, as you get closer to the robot, the X should not really go down. The magnitude of X should go up. So these numbers drop to negative numbers. So X in this case is proportional to inverse of the distance. If this is your distance here, then you should really use some kind of inverse measure of distance or reciprocal or something. So as you get closer, these negative terms get bigger and bigger and totally stop the robot. Okay? So these are those details you have to pay attention to. So this is the case of something right in front of you. You're going to slow down and ultimately stop. Now, what if something is on the left side or on the right side? Can you move away from that? Let's take a look here. So here, let's say there is something on the right side of the robot, and you're getting close to it. Ideally, you want to turn left and get away from it, correct? Will you? Well, remember, this one here is your V of right, and this one here is your V of left. If you make sure your V of right is bigger than V of left, then you would definitely turn left. So in order to avoid an obstacle on the right, you should make V of right be bigger than V of the left. Is that the case here? Yes. Why? Let's take a look here. So in this case, what we have is the sensors that are on the right side, they get bigger numbers, correct? Why? Because these two sensors that are on the right side, they are much closer to the obstacle. These ones on the left literally receive nothing, and these guys receive some very small thing. It's these guys that receive the big ones. And where are the weights for these sensors 6 and 7? You're right, these are the weights. So look, for the left one, they are big negative numbers. For the right one, they are small negative numbers. So the velocity of the right is reduced less than the velocity of the left. So right is going to be bigger than the left. So the system is going to maneuver and turn left, which is exactly what you want. And conversely, if the object is on the left, side of the robot, you want to turn this way ideally as you move on. So in this case, it's these two sensors, 0 and 1, that receive almost everything. And now look at their weights. You can see clearly that the weight for the right one are bigger negative numbers than the left one. So left is going to be reduced much less than the right. So left is going to go faster, right is going to go slower, and that exactly means what? That is exactly the meaning of turning right. So you see, it can easily handle the objects on the left, right, or on the front of it when it's going forward. If it's going backward, then you have to do a similar thing on these 8 weights. And basically, if you follow this table, which tells you if you have a small or big negative number for a sensor being where and a motor being where, what kind of behavior you are expecting, to steering left, to steer right, to just stop going forward, right? This is the overall guidance for this system, and you can see that also over here. So basically, for obstacle avoidance, give bigger negative weights to which sensors? To the sensors that are on the other side of the motor, and give the smaller negative numbers to the sensors that are on the same side as the motor or closer to the motor, and this will easily achieve obstacle avoidance and a safe navigation. And you can see the code here. So if you look, here is the initialization code, getting the sim for getting the robot handle, okay, through get object. Then one thing that you have here is using what we call a collection. What is a collection? I will tell you in one of the future videos under CoppeliaSim. So here you're adding all of the obstacles to a collection, okay? And these are the objects of the scene. And then you get rid of the robot out of all of them. So the collection here is only the collection of obstacles, not the robot, okay? Now you're gonna go and read all of your 16 sensors. Initially you start them as empty, but then you go under ultrasonic of the robot and get the values of the sensors, use sensors. Okay, you also get the handles of the left and the right motor. Now here, these are 2 parameters that you can tune, a 0.7, a 0.2. What are these? No detection distance, maximum detection distance. So this is the distance that the object closer than this is considered maximal. So any object in the scene that is closer to the robot than 0.2 is going to give you maximum reading, and any object that is further away from 0.7 is literally detected as no object. So basically the robot is seeing only between 0.2 and 0.7. Anything below 0.2 is considered a maximum. Anything above 0.7 is considered as no object. So this robot will only basically it reflect, right, or respond to the objects that are only within 0.7 meters of it. If you want the robot to stop much earlier before getting very close to anything, you can increase this number. So if you make it 2 meters, now it is going to start reacting to the objects that are 2 meters away, and it's going to slow down a lot earlier compared to getting very close to the boundaries of the object. Okay? And so here I start these detect signals at 0. These are the weights that I told you. This is the base speed, 2 meters per second. That is that bias. And then I don't need to do any cleanup, but in the actuation function, right? So look here, this was your initialization. In the actuation one, what would you do? You're going to go and read the proximity sensors for each and every one of those sensor handles that you created, U sensor I. And then this is the part that if they are less than maximum distance, you set them to the maximum, as long as they are within that no detection distance. Here you normalize them. And if they are outside that 0.7, you set them to 0. Initially, you start the motors both to V0, and then you apply what? The weights times these normalized inputs. And you do it for each and every one of the sensors. And once you have this V left and V right, you're going to pass them to what? To the motors using the command set join target velocity. So look here, when we run it, when it reaches almost within a block of the wall, it is stopping, or less than that. Each one of these blocks is about 0.4 by 0.4 meter. So in this case, once it reaches around 0.2, 0.3, 0.2, it is going to fully stop. And I guess that 0.2 was that max detection distance. Okay, so if you change that or change that 0.7, you are going to change how close it gets to the objects before it is stopping and basically changing the direction. So here, if I go into the code and make this like 0.1, okay, and if I go back with 0.1, look what happens. So I need to now go to 0.1 before I stop, okay? So you see it got a little bit closer. And if I go back and change it back to 0.2, but started to react earlier, so make this, I don't know, 1.2 instead of 0.7. So look what happens now. You see? At a bigger distance, it started changing the orientation, because now it can detect up to 1.2, not just 0.7. So using those parameters, and here you see it literally stuck there. Why? Because the distance that it can sense from some of these sensors is below 1.2, and they are big enough that they made the value of these joints literally negative, so they stopped at this moment. And this guy is completely what? Blocked. So if your scene does not have big gaps, it has narrow passages, you don't want to use a big number on that distance here, okay? If you make this distance too big, then you might not be even able to pass through narrow passages, okay? And if you make it smaller, then yes, you are going to what? You are going to comfortably get closer to the objects and pass through those. So this is what you want to consider. A good recommendation would be at least something as much as the width of the robot itself. Okay? And in this case, the robot width is like 0.4-ish something, 0.35, 34. So something bigger than that would definitely work. And you see it is getting close to the objects now as much as it can. And you see that once it passes this object, so those left sensors stopped reading, it tries to maneuver a little bit to the left, okay? So this is really a cool algorithm, I would say, instead of just doing a wall following or something. This Braitenberg, to me, is a very brilliant and yet simple method as long as you pick those weights properly. So hopefully this video was useful to you. You learned something. I'm going to share this script with you under video description. Just note that the script is not written by me. It's written by the people in CoppeliaSim. I just made it a little bit fancier, added some more comments on it, but basically that's what it is. Thank you, and I'll see you in the next video.